This presentation is to discuss some key design considerations for shunt voltage references used in secondary side regulation as a voltage loop error amplifier in an optocoupler feedback circuit. This video will discuss how a shunt voltage reference works, show how lower IREF and ILDEV can achieve better system accuracy, and talk about no-load power consumption standards. The shunt voltage reference, as shown in the circuit above, is normally used in secondary side regulation where it acts like a voltage to current controller to drive the optocoupler within the feedback circuitry. It senses the voltage output, VKA, via the resistor divider. Depending on the voltage level that it senses, the shunt reference can drive the current of the optocoupler higher or lower. This will then drive the comp pin voltage of the PWM controller, in which the controller will adjust its PWM signal to drive the output voltage at the secondary side accordingly. Please note that throughout this video, we will continually use the TL431 as our shunt voltage reference example, as this is a commonly used part number. There will be two kinds of TL431s mentioned, the TL431Li and the industry standard TL431. So how does a shunt voltage reference work in the system? Note that VKA can fluctuate high or low depending on the impedance at the load, and that resistors R1 and R2 are normally designed with high resistance to ensure low standby power consumption. In this example, let's say that the output voltage, VKA, rises above a desired level. The voltage at the ref terminal will increase. Taking a dive into the internal circuit of the TL431 as shown in Figure 2, this ref voltage is compared to the internal voltage reference. The op-amp output is used to drive the output transistor, IF, at a higher current. This higher current is transferred to the primary side of the system through the optocoupler. The comp pin of the PWM controller senses this voltage change and will adjust the PWM controller accordingly to drive down the output voltage of VKA back to its normal level. Let's now talk about output voltage error. The output voltage is given by the equation above. If a designer chose to build their circuit so that the output voltage were to be 5 volts and R1 was fixed to 10 kiloohms, then a calculation for R2 must follow. By solving for R2, the R2 value would be 10.1 kiloohms, accounting for an IREF of 4 microamps, while a resistor value of 10.03 kiloohms would result for an IREF value of 0.8 microamps. Since resistors come in discrete and standard values, most designers would select 10 kiloohms for their design. Since R1 equals R2, the error for VKA would focus only on the second portion, IREF times R1. Therefore, calculating the error for an industry standard TL431 yields 40 millivolts, which represents a 0.8% error of a 5-volt system. However, the TL431Li yields only 8 millivolts of error, equivalent to 0.16% of a 5-volt system. Note that in order to ensure low standby power consumptions, R1 and R2 are generally large at the range of 10 kiloohms or above. Additionally, a delta in IREF can cause additional error to the output voltage. Note that the delta between the typical and maximum value of IREF represents part-to-part variations across manufacturing. Since the error in VKA is related to IREF, as highlighted by the equation, a smaller delta in IREF can yield better performance. Comparing TL431Li to the industry standard TL431, the IREF delta is 0.4 microamps compared to the industry standard at 2 microamps. Calculating the error, the TL431 would result in a 20 millivolt spread, while the TL431Li would result in only 4 millivolts, which is a 5 times improvement. IREF can also vary over temperature and is specified in the datasheet as ILDEV. The absolute value of ILDEV, along with its delta, can also affect the output voltage accuracy as the error equation is related to IREF. This error to the output voltage can be minimized if ILDEV along with its delta is small. Comparing the industry standard TL431 to the TL431Li, the TL431 will result in a 12 millivolt of error across the absolute value of ILDEV and 8 millivolts of error across ILDEV delta. Devices such as TL431Li will yield only 4 millivolts across the absolute value and only 2 millivolts across the delta. Since IREF can vary with temperature, the maximum value of IREF will be IREF plus ILDEV as shown by the table on the right. The table in teal shows error calculations when using 10% and 1% resistors. Notice how the TL431Li is able to outperform TL431 even when using 10% grade resistors. This improved performance also comes with a cost savings on resistors, as can be seen in the chart below. Therefore, not only can a lower IREF and ILDEV spec achieve better system accuracy, but additional cost savings can be achieved. In addition to accuracy requirements, designers need to also take into account regulatory standards such as no load power consumption. Since 2004, countries and regions are requiring stricter rules for no load power consumption to count for the many power adapters and appliances left plugged in even when not in use. Even though the US is the only governing body to enforce Level 6 standards, many power supply manufacturers are adjusting their designs to meet this requirement to ensure universally compliant devices. Let's take a look into the Class 6 requirements. We will use the European Code of Conduct as an example. It specifies that for power adapters outputting power lower than 49 watts, the no-load power consumption needs to stay within 75 milliwatts. If we take a 20-volt output system, using TL431 with a regular optocoupler normally requires 2 milliamps in a biasing current for a practical use case. This will yield 40 milliwatts of power. Adding in all other component losses, the total no-load power consumption will easily exceed 80 milliwatts, which will disqualify itself for the European COC standard. By using shunt references like ATL431Li, with a high current transfer ratio optocoupler, one can bias that branch at only 200 microamps in a practical case. This will save 36 milliwatts of no-load power consumption and will qualify itself to the European COC. Thank you for watching. To learn more, please visit us at www.ti.com/vref, where you can find VREFs with different features, read our tech notes and blogs, and use the TI ETE support page to ask any questions.